In this video, I'm going to present creating formulas in testing forms. In multiple videos before, while I presented the design of testing forms, I was converting mathematical formulas into formulas that are understood by the program. But I never explained how this formula works, and I don't think it's immediately obvious how it works. Therefore, I decided to dedicate a video only explaining these formulas. So let's log in, and I will go to the form design for loss on drying. This one that it was presented in a video before, and I will take this as an example. Go to details, and we can see the form. There are several formulas here. So we have the measurements, and here we have the testing data used for validating this form. For start, let's take a formula. I will take this formula, I will copy it, and here I have prepared a formula playground to be able to experiment with formulas and to explain how they work on simple examples. But first, I will test the playground on this formula. I'll paste it in here, and we see that we have some parameters. What are these parameters? We will use this parameter, this parameter, this one, and these are the values. So we will copy all this data, which are the input data. These are the direct measurements. We will copy into the playground, and I will paste them in here. Make this larger. As we can see, the formula we have introduced in here has already been evaluated, and this is the result in here. And as we can see, these are the same values as those in the verification form in here. However, for now, we will just clear the playground, and let's start with very simple examples to try to explain how this formula works. What is a formula? Let's start with something very simple. It's a scalar value. We can see here in the result the displayed value. It can be the result of an operation. We can have arithmetical operations, additions, subtractions, divisions, We can group operation by using parentheses. We can have exponential. So these are the arithmetic operation which are pretty similar with the usual mathematical operations. Let's talk about logical operations. We can have 43 is not smaller than 13. It's greater than 13, so the result is 0. 0 means false and 1 means true. So 43 is bigger than 13, so the result is true. Formula is working always with numeric values, always. We can have OR operator, or 34 smaller than 2, which is correct because one of the two should be true and the first one is true. Okay, or we can have logical operation AND. In this case is false. Now is true. Both operands are true, therefore the result is true. We can have also built-in functions like for instance square root. Square root of 9. We have round method. In this case, when there are no other parameters, it is rounded to the closest integer without decimal places, but we can specify the number of decimal places we want. The default value is 0. Sometimes formulas are very complicated, and it's useful to be able to split a larger formula in smaller chunks, easier to read and to understand. In this way, it's easier to find mistakes. So we can use for this purpose local variables, like for instance, let's say we have this expression, but we want to, for a simplification, we want to introduce a local variable. We will call it A, and we will define it. And the result is the same. Also, because the result is the same. It doesn't matter how many intermediary calculation we have. The formula returns always the last line, the last calculation. This is the result of the formula. For instance, we will comment out. This will be just a comment now. And we want to see what is the value of a local variable. And this is the value for local variable a. Because this formula, it is used in testing forms, it's important to have the possibility to provide external parameters for calculation. For instance, I'll name this B. I use square brackets to define an external input parameter, and I will define it in here. And we have the same result. Until now, we worked only with scalar values, but now I want to give some examples of vector input parameters. Let's say the vector parameters are always in double square brackets. This is the differentiator from the scalar values. Let's see what operations can we do this with this vector parameters. I will comment this for now. And let's see. We can return the value immediately. We can do arithmetic operations. So I have performed an addition between a vector and a scalar value. And the result is that each element of the vector was added the scalar value. I can perform division, and each element of the vector was divided by 2, and all other mathematical operations. Now, the result of this operation, it's a vector. We can use in this expression a scalar from parameters. For instance, and every element of the to every element of the vector was added value of the external parameter. We can also use a local variable, this one. And now to each element of the vector was added the scalar value represented by the variable a. For instance, I showed earlier the function, the scalar function square root. In this case, the result is, if we use as an argument a scalar value, the result is a scalar value. But if we use a vector value, the result, it's a vector containing the square root of each vector element. In these operations, it is always important that the vectors have the same size. For instance, we will add a new one. If we try to add these two vectors, element 1 is added with element 1, element 2 with element 2, so on and so forth. If we put one more element here, we have an error. They are not accepted in an expression vectors of various sizes. You can always have vectors of the same size and scalar values, but not vectors of various sizes. For instance, we can use a scalar value here, and the order of operation will be like this. If we want to change the order of operation, we can do it like this. So first, the parentheses are solved, and the result will be a vector divided with a scalar. It will result a vector. Now let's return to our initial use case, and take this formula again. I'll clear the form, take the formula, close. Now I will take this data, which represents the parameters of the form, and I will add it in here. And again, we can see the same results as in the form. We can check this in here. Let's play a little bit more with these formulas. I will take this one, but just, okay, I will take everything, close, and I will add it in here. I will delete this comment, and I will replace this vector parameter with a local variable. And now we have 0.4 is the mean moisture result, which is right in here. mean moisture result. And the one before was sample moisture. Is this one? Okay, let's continue to get more formulas. Let's take this one. For calculating standard deviation, I will add it in here. The mean moisture is this one. I will add it in here and remove the parameter brackets. I will add this. Also, I remove this brackets. And for this one, I will take it from here. And I will remove the brackets because now it's a local variable. This is the sample count. And we will remove this brackets. And the result is, for standard deviation, zero point 0.032. This is the standard deviation. And we can see it in here, 0.032. The sample count, this one, the sample count is 5, correct, is this one. The standard deviation, we already seen it, 0.032, 0.032. The mean moisture, it's 0.4, is this one, 0.4. And again, the sample moisture, the individual sample moisture is 0.4, 0.38, 42, 44, and 36 is this ones. I hope that this demonstration will help for a better understanding of designing formulas. Please share your thoughts in the comments below. Please like, subscribe. Bye.